All right, the next concept we're going to tackle is reducibility and irreducibility. So let me start with just the definition. The definition of irreducibility and reducibility is as follows. A non-constant polynomial over a subring, usually this is going to be a subfield, R of C, is reducible basically if it factors. So if it is a product of two polynomials over R of smaller degree. Factoring, whether or not you can be written as a product, doesn't involve division directly, at least. So being reducible is, we don't have to state it necessarily for subfields. It's a general thing for rings as well. And we'll often look at the ring Z sitting inside of C. So although we will care about it for fields, being able to reduce to being able to look at it over rings is going to be helpful, as we will see with some of our results here. Okay, so that's what it means to be reducible. That is, if you can factor it. Otherwise, it's called irreducible. And irreducible polynomials over when it's over a field are the ones where you mod out and by them and you get a field again. So so if you look at a polynomial ring over a field and you have an irreducible polynomial, you look at the quotient ring, you get a field again. So we won't deal with that right now. We're going to mainly focus on trying to determine if polynomials are reducible or not. But later on, this is going to be very helpful. So keep that in mind, that this is not just we're playing with polynomials. There's some algebra that's going on in the background. So let's do an example, a series of examples. Any polynomial of degree 1 is irreducible. In fact, degree we saw takes multiplication to addition. So if I have a polynomial of degree 1, it looks like at plus b. If we were to be able to factor it as f times g, then we could apply the degree to both sides. On the left-hand side, if it's a linear polynomial, degree 1, a is not 0, so this is degree 1. On the right-hand side, degree takes addition, or multiplication to addition. Degree, though, neither of these can be negative infinity, so f and g are both non-zero, certainly. And the degree is a natural number, so it can either be 0, 1, 2, or so on. The only way that two natural numbers add up to 1 is if one of them is 1 and one of them is 0. So this would tell us then that the degree of f is also 1. So at plus b cannot be written as a product of polynomials of smaller degree, because 1 and 1 are the same. So this one is the same as the degree of at plus b. So it's not smaller. All right, so all linear polynomials are irreducible. That's our example A. Let's look at some quadratic polynomials. So the claim is t squared minus 2 is irreducible over q. So here our subring happens to be a field, it's q. So how do you prove something like this? Well, suppose, what does it mean to be irreducible? It means that you're not reducible. So we're going to go for a contradiction. So suppose you could factor t squared minus 2 as a product of polynomials of smaller degree. The degrees have to add to 2, though, as we just saw, and they have to be smaller than 2. The only way to get two numbers, natural numbers, that add to 2, such that they're smaller than 2 is if they're, in fact, linear polynomials. So the only way it could possibly be reducible is if it factors as a product, at plus b times ct plus b, and that's the only way. So suppose for a contradiction, again, let's be a little bit more clear, it is reducible. And again, the only possible factoring is this one. All right. The coefficient of t squared is a 1, really. So we can actually assume that a and c are both 1. So I'm going to do that right now. All right, so t plus b times t plus d should be t squared minus 2. And the question is, can you find a b and d that makes it work, or can you deduce that no such b and d work? Well, I don't know. Let's multiply it out. If you FOIL it out, you get t squared plus b plus dt plus bd. And then on the left-hand side, that's t squared. There's no t's over here, and then minus 2. So for these guys to be equal, b plus d had better be 0, and b times d had better be negative 2. So let's write that out. So we get a system of equations. B plus d is 0. B times d is negative 2. The first equation is really b is negative d. And we can plug equation 1 into equation 2. So if we plug in b is negative d, we get negative, oops, I don't need a parentheses there. I'm going to replace my b with negative d. We still have the d, and that should be negative 2. This tells us d squared is 2, which tells us that d is plus or minus root 2, which is a contradiction. Let's use a blue lightning bolt to mean contradiction in this class. I'll just be clear this first time that it means a contradiction, as plus or minus the square root of 2 are not rational numbers. So if we had access to the square root of 2, maybe by adding in the square root of 2, this would now factor. But we don't have access to the square root of 2 because we just have rationals. So this is an irreducible polynomial. Why? Well, we thought we suppose it was reducible, and we got to a contradiction. So it must be that t squared minus 2 is irreducible. In fact, t to the n minus 2 is always irreducible. Okay, great. So it is irreducible over Q. However, let's do just to indicate that really where you're checking matters. The polynomial, how do I say this? The same polynomial is reducible actually over R. Well, why is that? Well, over R, t squared minus 2 clearly is going to factor as a difference of squares, t minus root 2, t plus root 2, which is the factoring we kind of found above. So it will factor that way over R, and this tells us then that, or thus it's in fact reducible. Sorry, I'm going to probably confuse the words reducible and irreducible. It should be clear what I mean by context. Namely, we can write it as a product of polynomials of smaller degree. That's exactly the definition of being reducible. All right. Great. And then the last example in the textbook, and this is where the definition we have of irreducible polynomial is maybe not quite the same as irreducible in general, and that's okay. As far as we're going to need it, this is sufficient, although it's not 100% correct. So, for example, 6t plus 3 is irreducible over z of t. Well, is irreducible over z. And the reason is, well, it's a linear polynomial. And we agreed that linear polynomials cannot be factored as a product of guys of smaller degree. But notice that this actually kind of has an interesting factorization integrally. 6t plus 3 is 3 times 2t plus 1. Neither of these are units in z adjoin t, and so this is a factorization into non-units. If you remember your ring theory, you know that to be irreducible, the only possible factorization is when you sort of pull out a unit. But neither of these are units, and nevertheless, we consider this, are going to be considering this polynomial irreducible. Okay, so I just want to make that distinction right now. This is not quite the correct definition of irreducible.